Hello, my name's Adam. Thank you for joining me on my continued series of understanding modern poker theory, where we attempt to understand this book, Modern Poker Theory, but also just the overall concept of modern poker theory. So today we are going to be doing a example. This is all we're doing in this video because it is a kind of long example. We are going to be going over the indifference principle. This is where we left off last time, as you may recall. This is our definition. I'll let you read that yourself. It is the biggest thing about this is if a player plays a mixed strategy at equilibrium, it must be that all actions he takes with a non-zero frequency have the same EV. And this principle is intimately connected with the idea of balance. And making your opponent indifferent is a very key concept to understanding poker theory and whatnot, and the theory of playing poker from a GTO standpoint. Because, well, you win the pot. As we'll see in this example, it's actually very powerful to make your opponent indifferent. So let's go ahead and just get into it. This is the clairvoyance toy game. So first off, a toy game is a simplified example to examine a specific scenario very narrowly. They are a thought experiment used to study extreme examples with the explicit goal of learning more generalized concepts of the game. It's important to understand what this is. It seems, just in my experience, people who I've talked to who have read this book and not understood it, whatnot, they seem to get stuck on the concept of a toy game, at least some that I have spoken to. In a very real sense, what we are doing is what your solver does. You know, they do it much more complexly. They have a lot more variables, but all they are doing is running this scenario over and over and over and looking at the output and calculating the EVs and seeing if it's positive or negative or which one's higher. That's all it is doing. So it is important for us to go over this and understand what is happening and how we calculate these EVs. Now, one thing that's important to understand about this example and all of our approaches, we're assuming that we don't know anything about the game. I'm going to be giving you our variables, our assumptions. Yep, there they are. And this is what we know. We know the basic mechanics of the game, and we know this. So I think it's important to delve in because we are trying to build a whole strategy essentially from scratch. We're not trying to go with anecdotal evidence or whatnot. We're trying to figure out, and we do that through things like toy games. And like I said, this is effectively a very, very basic solver. So let's go ahead and go through this. Let's start with going over each of our assumptions. In this particular hand, we're going to be analyzing a hand on the river. It's going to be involved between two players, which we're going to call player 1 and player 2. There's going to be a $100 pot that is already in the middle, and then each player will also have $100, or at least the effective stack will be $100. So at least one of our opponents, or one of our players only has $100. We are on the river. Player 1 has a range of ace-ace or queen-queen, and that is it. That is their entire range. But it's even worse for player 2. Their entire range is king only. That's it. This is their entire range. So that is one of our simplifications. Remember, we're going with a very simplified example. This is our board: 3 3 3 deuce deuce. Okay. Player 1 is out of position and player 2 is in position. And also importantly, this is a true Nash equilibrium discussion. Both players are clairvoyant and they know each other's entire strategy. So player 2 knows that player 1 can only have one of these two hands, and player 1 has even better position. He knows his opponent's exact hand. Remember, to be clairvoyant does not mean that they know the exact hand, but if they know their entire range and their entire range is one hand, then they do. Okay, so as we've defined it, player 1 has a polarized range where ace-ace is the nuts and queen-queen is air. So this particular example, this is coming straight out of the book, and these are the ranges and hands he uses. I've seen earlier versions of this exact example that we're going to go over, but they use different hands. They use like 7 deuce for air or whatever. I like I like this particular setup because it does drive home the point that these concepts like polarized range, nuts, air, condensed range, these are all relative terms. So in this scenario, queen is air. It's a bluff because our opponent always has king. And king is a condensed range and a bluff catcher range because he never has the nuts, which is ace, or I guess a 3 in this particular spot. None of those hands are in the range. And we'll see exactly why king is a bluff catcher. We'll actually show that mathematically, but it's because, it can beat the queens, but not the aces. So this is all we know. Let's apply some game theory principles. Actually, let's see which questions we are. So what is each player's range versus range equity? Well, at showdown, player 1 will win half the time that they're holding ace, and they will lose the half the time they are holding queen. So thus, each player's equity is 50%. Okay, they have 50% equity, but they do not have the same EV. So we're going to be calculating the EV just like a solver would. All right. So at showdown, ace always wins. So therefore, the EV of calling a bet with ace is equal to whatever's in the pot plus whatever the bet is. So if our player 2 with kings ever bets and player 1 calls with ace, they will always win this amount. Okay, the EV of folding ace is equal to 0 because the EV of folding is always equal to 0. That is one of our definitions of EV. We'll come around to that some more later. So this is where we get into things like dominated strategies. Folding is a dominated strategy and should never be used, right? You can see that mathematically because the EV of folding is 0, and this number, we don't know what this number is, but we know it's always positive. It is always, you should never fold. We'll get into this, obviously, like if there's money behind and you have the ace and you know it's always good, you should make sure you get it all in, but we're not there yet in this example. But folding is a dominated strategy, so we will never fold ace. Now, conversely, queen can never win at showdown. So the EV of calling with queen is you lose. You minus the bet. Whatever the bet is, whatever bet you call, you lose, and you never win the pot. So it's always a negative number. And EV of folding queen is, again, always 0. So calling is the dominated strategy when you have queen. So you never fold ace, you never call with queen. So since player 1 will never fold with ace and never call with queen, therefore betting king is a dominated strategy and should never be used, right? Because if player 2 bets with his king, then player 1 will always continue, will always call or raise with their ace, and they will always fold their queen. So that is your dominated strategy over here. So we'll never bet with king. Since player 2 will never bet with king, but may call a bet from player 1 should always bet ace. Checking with ace should never be used. It is a dominated strategy. It's going to be EV of 0 as well because they would be closing the action and going to showdown. And then the EV of betting would always be higher. All right, so what is the optimal bet size for player 1? How often does player 1 bluff with queen? How often does player 2 call with king? And what happens if the positions were reversed? All right, so these are the questions we're going to be asking or answering. They've been asked. There they are. They're asked. So let's answer these questions while we also will be calculating the EV, which was the core question, the initial question that we were being asked. All right, so if player 1 always bluffs all in with queen, as well as value shoves ace, then player 2's EV can be calculated as follows. So the EV, so we saw this before, that the EV of shoving with ace is going to be 200, right? It's pot plus bet, so the pot is 100, the bet is 100, and they're going to have ace half the time. Then you have to subtract that the EV of shoving with queen is you lose the bet. All right, so half the time you lose 100. So the EV of shoving the entire range is $50. Okay, which is the same as the equity. All right, because they're just always getting to showdown, right? Because if player 1 is shoving their entire range, then player 2 has to call with everything. That's right. This is where I'm getting confused. So player 1 is the one shoving. We are calculating the EV for player 2. That's why this looks like this. So he's calling 100% of the time, and he's winning. This is the half time you have queens, half time he has aces. Anyway, so EV is 50 of always bluff calling. I don't know what these variables are supposed to be. But whatever. That's of this scenario is $50. So if player 1 never bluffs with queen, then player 2 would never call with queen, because player 1 is still always betting ace, but never queen. So the half the time that player 1 bets and player 2 folds, and the other half player 1 checks and player 2 checks and always wins a showdown, right? Because that's which positions they're in. So anytime he bets, he knows he has aces, so he folds. Anytime he checks, he knows he has queens, so he just checks because he's never calling with queens. And again, the EV of this scenario is also $50 because it's just the same as their equity. It's they're doing everything with their entire range. So if player 1 always or never bluffs, player 2's response is trivial. They will simply call or fold appropriately. Remember, player 2, they're clairvoyant. They know the entire strategy. So whatever strategy player 1 comes up with, player 2 knows that they're doing that. So player 1's goal is to make player 2 indifferent to calling or folding. They don't want their decision to be trivial. They want it to be indifferent. Okay? Let's see what that looks like. So to make player 2 indifferent to calling and folding, player 1 must bet in a way so that the EV of calling is the same as the EV of folding. Okay? That's the whole goal right here, is to make these the same, because when the EVs are the same, then you can employ a mixed strategy and you're indifferent. See? It's all coming together. Now, the EV of folding is always 0. So we know that the EV of calling, which is equal to the percent of the time you win times the amount you win, minus the percent of the time you lose times the amount you risk, and we set that to 0. Okay? Now we're going to do a little bit of math. We're going to do a little bit of pure algebra. I should have warned at the top, this is our one of our more math-heavy videos, but it's all just algebra. Just doesn't look so clean on the sheets. We'll go step by step. But anyway, so we substitute like this. Percent of win, we give it the variable of W. The percent lose, we'll give it the is equal to 1 minus the variable of W. Money won is equal to B plus B, where B is the variable is equal to bet, and the variable P is equal to the pot, and then the amount you risk is the variable of the bet size. Okay, so we just plug this into this, and we get this W times B plus B minus 1 minus that. Do some algebra, and you can solve for W, the percent of the time you must win, and you get this formula. B divided by 2B over P. Plugging in our numbers, we have our $100 bet. That's our all-in bet. Divided by 2 times the bet, which is 200, plus our pot size, which is 100, gets 1/3 or 33% of the time. So this is the same number as the pot odds on a call, which, if you remember the definition of pot odds, which is risk over risk plus reward, this is just me calculating. Yeah, this is the equation for pot odds. But if you remember the definition of pot odds, you would not be surprised by this result, because pot odds is defined as how often you have to call in order to break even. So as to player 1 to make player 2 indifferent to calling or folding, he must bet with a frequency equal to player 2's pot odds. Okay? Should all make sense from what our understanding of poker math to this point. So what we need to do is determine how often player 1 has to bet queen queen to make it so that their range is 67% value and 33% bluffs, right? So that makes sense, right? So in order to allow player 2 to win 33% of the time, player 1 has to have 33% bluffs. Okay, so your bluff percentage is equal to bet over 2 bet plus pot. All right, try to look up where exactly this equation comes from. They just listed it in the book, but we'll say bluff percent is bet divided by 2 bet plus pot. Is that the same? Okay, it's just the same as our win percent equation. We're just substituting it here for a new variable. All right, so bluff percent equals bet divided by 2 times the bet plus pot. The value percent is the inverse. So you find the inverse by doing 1 minus the bluff percent, right? And then you do some math. If you plug these numbers in, you basically put this in here and you simplify this out, you get this equation, bet plus pot divided by 2 times the bet plus pot. Therefore, the bluff to value ratio, the bluff to value ratio would be bluff percent by value percent, because that's how a ratio works. But then if you take this right here and then divide it by this right here, then you get this right here. Bet divided by bet plus pot. That is the bet to value ratio. So this is where our therefore should be. So in this spot, $100 bet, $100 bet plus $100 pot equals 1/2 or 50%. Therefore, what that means is player 1 should have 1 bluff for every 2 value combos, and therefore should bluff with queen queen at a 50% frequency. So half the time he has queen queen, he bluffs. Half the time he has queen queen, he just gives up. Player 1 has ace ace at 50% frequency and bets them at 100% frequency, as well as queen queen at 50% frequency and bets them at 50% frequency. Therefore, 75% of the time they're betting, and then 100 minus 75, you get 25% of the time they are checking. Okay, so this is how often player 1 has to bet their range in order to make player 2 indifferent to calling or folding. So let's start to put it all together here. Let's do our EV calculations. Remember, this is our main question we were trying to answer, is what are the EVs of every scenario. So ace ace has the EV of when player 2 folds times the percent of the time the player 2 folds plus the EV of player 2 call times the percent the player 2 calls, right? Makes sense. So when player 2 folds, the EV of betting ace ace is 100, because you just win the pot. So half the time you just win the pot. Plus when player 2 calls, you get $200 because you get the pot plus the bet, and you get that half the time, which is $150 an EV. So queen queen, when they bet, their EV is 100 times half plus negative 100 times half. So basically, when this is the same thing, I just skipped this step here, right? So the EV of player 2 folding is 100. And the percent of the time a player 2 folding is 50%. And then the EV of player 2 calling, you have queens, is negative 100 times 50%. So queen queen bet has an EV of 0. Queen, queen, check also has an EV of 0. Queen, queen's EV is 0. Because whether they check or they bet, their EV is 0 in this scenario. So player 1's EV is the ace-ace EV times the percent of the time you have ace-ace plus the queen-queen's EV times the percent of the time you have queen-queen. So ace-ace, you make $150 half the time, and queen-queen, you make 0 half the time, for a total EV of player 1 of $75, which, as you may notice, is actually higher than their equity by a significant amount. Their equity is $50, but their EV is $75. This is the power of having a polarized range. That's why it's so popular. So then we do the EV of player 2 calling. So when player 2 calls, 33% of the time, they are going to be up against queen-queen, and they're going to win $200. Okay? 67% of the time, they're going to be against ace-ace, and they're going to win $100. This is the ratios that we did. Player 1 set up their strategies such that this is the ratio that they're betting. So player 2's EV of calling is 0, which is good because we designed that specifically. The strategy that player 1 was employing was specifically so that player 2's EV of a call would be 0. So if player 1 plays their equilibrium strategy, it does not matter if player 2 calls or folds, because both actions have an EV of 0. However, player 2 must call at some frequency, because if he doesn't, player 1 will adjust and will start to bluff more. If player 2 is never calling, then player 1 will slip back into just jamming 100% of the time, and he'll make everything. His EV will go to 100 if player 2 continues to fold always. Player 2's optimal calling frequency is one where player 1 does not make any money by bluffing queen-queen. In other words, player 1's EV of bluffing is equal to player 1's EV of checking, which is equal to 0. So this gets us into the topic of minimum defense frequency, which we actually are not going to go too in-depth in this example. I'm just going to give it to you for now, which is pot divided by bet plus pot. We're going to dive more into depth into what minimum defense frequency is later in the course, but in the meantime, in this example, what it just means is, so player 2 has to defend 50% of the time, or player 1 can adjust away from an equilibrium strategy and start over bluffing. Right, so we have a pot of 100 plus a bet of 100 plus a pot of 100 gives us the 50% ratio. Again, these are all numbers based on this exact example. If you have different pot size and bet sizes, these numbers will change. So player 2 has to call with king-king 50% of the time to make player 1 indifferent to bluffing. So player 2's optimal strategy is to just, seemingly at random, we'll talk about randomization at some point, but at random, just decide half the time they call with king-king and half the time they don't. And that's the only strategy that they can have to, this is the best counteraction they can give to player 1's strategy in this scenario. MDF tells you how often player has to call. You can also approach from me. Yeah. Yeah. I don't know. It's been a while since I made these slides originally. I don't think we have to get too delve deep into alpha or MDF just yet. We will be talking about them in the next section and use them throughout the course. So we'll get into those concepts later. So when we put it all together, we can see that player 2's EV of calling is equal to 0 because player 1 has made that happen. And player 2's EV of folding is also equal to 0 because that is the definition of folding. Player two's EV when it goes check, check is he wins $100 in the pot, and 1/4 of the time that happens, right? Because 100% of the time that player one has aces, he bets, and half the time he has queens, he bets. So 1/4 of the time he just checks, and then player two can check and win his $25. Player one has effectively stolen half of player two's equity by making, by using the indifference principle and making player two indifferent to calling or folding. Player one has effectively stolen half his equity. So good on you, player one. So let's go through. So we've answered all the questions except for the position. And in this particular scenario, which is a pure nuts air, perfectly polar versus a bluff catcher scenario, position does not matter because, as we talked about initially, betting king-king is a strictly dominated strategy. Regardless of position, player two could never bet his king-king because player one can simply just respond perfectly, fold all the queen-queen and call off all the ace-ace, and it doesn't matter. So in this particular scenario, if they were to switch positions, player two would then just have to check and then check call at a 50% frequency for all the same reasons as he had to in this particular scenario. And this is another subject that we'll really delve into much deeper later in the book, but player one's range is perfectly polar. The optimal bet size is always all in. We kind of just assumed throughout the example that the bet size was all in, but with a perfectly polar range that you want to go large, and it's theoretically all in. Oops. Well, that's as far as we're going in this particular video. That is our example. We will start out our next video talking more on MDF and alpha. We'll go into what those mean a little bit more and a few other subjects, but this is definitely enough for one video for me. So that is the clairvoyance toy game and understanding the indifference principle. I hope it's a little bit more clear to you. And one thing I like about this example is it really does show the value of the indifference principle, because again, we go into the equity of each player had was $50, but player two just gets screwed in the scenario, and there's nothing he can do about it because it's just the scenario that he's in. He's got a pure bluff catcher. That's the problem. The problem of finding yourself on the river with pure bluff catchers. I would sometimes it happens, but it's better. It's definitely always better to be the guy that's betting polar and making you indifferent. That's definitely where you're going to make your money. So seek those spots for sure. But anyway, that's all I have today. Thank you for joining me. Again, my name is Adam. Please leave a comment. Let me know what you're thinking about these formats, what I can do to improve these. Still very rough and raw, but we'll get better. This is an ongoing project, and I fully expect to get this looking better and cleaner eventually. I'd ultimately like to come back and just redo these better animated, making it a little easier to follow along. But for now, this is what I can give you. So thank you for joining me. I appreciate your time and in consideration. Please leave a comment, like, all those things. They do help, especially me. Like, leaving comments help for me to know where I'm completely screwing up and what I can do to make it better. But thank you, and I will join you on the next one where we will, like I said, we will go into more of this MDF and alpha, as well as some other topics as well on that one. So I will see you then. Thanks.